Bonsoir. This is the only thing I will say in French. I would like to say how grateful I am to the organizers to have taken the risk of inviting me. I am not a medical doctor and I do not promise any efficient thing, but maybe we can share a few things concerning the brain. And the essence of my talk will deal with a general idea. The idea is that the brain simulates action. It's a simulator. And the provocative title I gave to my talk says that so-called sensory or motor deficits may be due to deficits in this projective simulation of action and close relation between perception and action. Because we know now that there is no more any frontier between perceiving and acting. And one of the beautiful examples, as you know, is the discovery by Giacomo Rizzolatti and his colleagues of the mirror neuron system, for which they actually got the Brain Prize recently. So our brain, in addition to I have to learn how to use this thing. In addition to dealing with sensory information and transforming into action, has internal loops, like basal ganglia, thalamocortical loops, etc., for physiologists, which allows him, or it, or him, to simulate action, to choose, to decide, eventually to change. Also, the brain does not take the world and perceives from senses. It imposes on the world its rules. For instance, you perceive here two little creatures which you think are of a different size. But if you go to the screen, you will discover that on the screen they have exactly the same size. It is because our brain imposes on the world the interpretation given the context. So these are just two general ideas I wanted to say to introduce the things which I like to share with you. So the main ideas of the talk are that evolution has designed mechanisms for perception and action which are not simple. They are what I call simplex. Some of these mechanisms, like simulation of action, anticipation, internal models, top-down control, etc., are actually mechanisms which use principles like detours. They are apparently complex. But through these detours of apparent complexity, they allow our brain to go quickly and solve problems. And for rehabilitation, I propose to you, because I have no way to say if it is applicable totally, it is to these apparently simple mechanisms that eventually rehabilitation has to address, and my talk will try to show you a few of these examples. Therefore, understanding and rehabilitation of so-called sensory or motor deficits has to address these cognitive, or what we can call cognitive mechanisms. Now, I'd like to give you about 5 or 6 examples of some of these principles and eventually suggest to you if they may be interesting to find new ways, because this is a challenge that Jens and his colleagues have given to us, new ways to actually orient rehabilitation. Vicariousness, it's a horrible word. My editor did not want to put it at the title of the book. Complexity, they say it's not la vicariance. The vicar is the replacement of the priest, as you know. The idea is that neuronal plasticity is an answer to lesions, but functional plasticity or substitution is another solution. The idea of vicariousness is that in case of lesion, the brain does not try to repair the lesion system, even through some plastic, beautiful mechanism like Michael showed. It will look for new solutions using the repertoire of available sensory motor systems. Example. For many years, I have studied the neural mechanisms of eye movements. We know we have reflexes, like the vestibulocular reflex, the optokinetic reflex, which stabilize the image of the world on the retina. We have the saccades, which is what you are doing to these slides at the present time. We also have pursuit, which is what you are doing if you follow my laser beam here. Now, these neuronal mechanisms, which we know, constitute a basic repertoire of gaze control. Now, with Jeffrey Melville Jones here in Canada, many years ago, in 1966, put some Dove prisms in front of a subject. These prisms reverse the apparent movement of the visual world, so that if you turn your head to the right, the visual world normally turns to the left. With the prisms, the visual world will turn to the right at twice the velocity. This kills completely the vestibulo-ocular system, as if there was a lesion. And what happens? He showed that after 6 weeks, the brain was able, by some plastic mechanism, to reverse the VOR. With him in Paris, and with a very brave student called Annick Béguet, who worked this Dove prism, we showed that this can be done in 1 second. If you look at this recording here, during an eye-head movement, there is first a saccade, then a head movement. This is a classical pattern of coordination of the eye and the head. But look what happens with the prisms. At first, the subject loses the target, of course, because all these reflexes are completely non-functional. And after 1 second, this is 0.5 second, the brain generates this movement here, which is at twice the velocity of the head and exactly what is needed to keep the target. This is what I call substitution, vicariousness. The brain has inhibited the non-functional VOR and immediately replaced it using combination of other sensory motor systems. Very beautiful. That is an example of this type of mechanism. Now, in this type of mechanism, inhibition plays a very major role. You know that most of the areas of the brain which are important for decision, for coordination, cerebellum, basal ganglia, prefrontal cortex output, many of these areas use inhibition. They are inhibitory. And that is another example I took on purpose, not from a motor task, but from a logical task. It's a beautiful work done by Olivier Houdet. Sorry, but I just keep in Paris. He's a specialist of child psychology, and he did the following experiment. He gave to children and to adults a perceptual logical task. I have no time to go into the detail, but the person had to make the logical estimation based on a perception of an array. At the beginning, the subject made errors, and the brain, it's a beautiful paper in Nature, and the brain activity was in the parietal cortex, visual parietal cortex, perceptive. And after a while, suddenly, that is the beauty of this experiment, the subject did not do any more logical errors, and the brain activity shifted to the prefrontal cortex. So that is one example of a vicariousness by inhibition. The subject had to inhibit the perceptive strategy, exactly like children when they grow up, they inhibit the first primitive strategy many times, like in la numérosité, etc. And they replace it by another system. So that is a beautiful example, which may be also inspiring if one tries to do some rehabilitation. Now, this flexibility and creativity of the brain, we can suggest, should be allowed. And that is my own problem, although I am not a clinician. I have a problem with many of these machines, which now invade the world of rehabilitation. And because I have the feeling many of these machines readapt the patient to the machine, but do not let the brain have the ability to create eventually a completely different solution. So that is just a suggestion that I would like to make very modestly, because it is not my job. Now, another example that may lead to thinking about in this area, locomotion. Locomotion is an incredibly complex mechanism. Hierarchical organization, pattern generators in spinal cord, initiation, mesencephalic reticular formation, repertoire types, integration with posture, integration with, and etc. Decision-making, knowledge-based integration of context. That is what it is to walk. To walk is not to do this. To walk is to generate trajectories, make decisions, take into account space and others, etc. It is simplified by simplex mechanisms. For instance, the question, is locomotion controlled bottom-up, from the feet up, or top-down? A number of years ago, with Thierry Pozzo, we have shown that actually a simple solution, beautiful, has been found by nature over evolution to simplify the coordination. This is the creation of a mobile reference frame by head stabilization. In other words, the child starts walking like this, taking the ground as a reference, bottom-up area. But we don't. We control locomotion from the head down. This allows us to free ourselves from the ground, to surf, to ski. To use, the head is used as an inertial guidance platform using the vestibular system in order to orient the head, and gaze to anchor the head inertial platform on space. I have no time to go into the detail. This has been published many years ago, and I have talked a lot about it. But it means that eventually, I suggest, many of the so-called motor deficits of locomotion are not motor. They are deficits which are due to this difficulty by the child to make this Euclidean transformation of going from a bottom-up, ground-referenced locomotion to a top-down vestibular and gaze control locomotion. And what has to be rehabilitated is this capacity of this top-down controller. That is another example. And this appears in the child between 2 to 4 years. So it is a crucial time eventually to look at what is really happening. Another suggestion in these 30 minutes is the similarity of simplifying laws between arm movements and locomotion, the global aspect that we heard about this morning. Jens insisted upon this. And which may lead to the idea that if you rehabilitate arm movements, you rehabilitate also the capacity to locomote. An example. A simplifying law, the one-third power law for movement. If I do this with my finger, if I draw an ellipse, there is a very, very strict relation between the tangential velocity and the radius of curvature. And this relation, as you can see here, once more. This relation here is so strict that eventually it also means that you go fast here and slow here. This is true for all movements of the arms when they are natural movements, and you know about biological motion. You can recognize natural movement by just a few dots on the screen. The interesting thing is that this law also constrains perception. If I do this, and I ask you, is my finger movement at constant velocity? You will say probably yes, but it is not. You will only perceive it at constant velocity if it is not at constant velocity and if it obeys this law, that I slow down, curvature is higher. So there are laws which subserve our generation of natural movements, which are probably, and I have no time to go into that, linked with the geometries that the brain uses. And we are now working, there are many discussions about which are the causes of these laws, minimum jerk, or we think with Daniel Benkin, we have published papers saying that the brain actually uses non-Euclidean geometries, etc. But it means that what eventually is disturbed is not the muscles. It is the generation in the brain of the adequate geometry. And one eventually has to work at this to allow then the muscular system to perform the adequate movement. What is interesting, it's also true for locomotion. If I go like this, in ellipse, if I generate a locomotor trajectory, the same law applies, which means that hand movements, actually Viviani showed eye pursuit also, and locomotor generation are subserved and controlled by the similar laws, which are cognitive mechanism in the brain using geometries and generating this trajectory, which then are implemented by the body. Ça va? Another example. The coplanar variation. It's been shown by many of our friends that if I do this with my hand, there is a very strict relation, co-variation between the elevation angles of my arm and forearm with respect to the vertical. Phase locking. This phase locking is true for arm movements, and it probably means that in the spinal cord there are coordination mechanisms which allow the brain to only control very simple variables. And this coordination is made down by mechanism in the spinal cord. The interesting thing here again is that this coplanar variation is also true for locomotion. It's been shown by a number of people, and particularly by our friends in Italy, like Juaniti, etc., that if I walk like this, there is also the same relation between thigh, shank, and foot elevation angles. Okay, so they are tightly correlated during locomotion. Same law for arm movement, natural, and for locomotion. And this develops in the child. The question is genetic or learned. Actually, there's a beautiful paper by the Italians, Ivanenko. There was also a paper by Chéron in Belgium, which shows that in the toddler, this coplanar variation, which is clear in the 7-year-old child, you see these three angles go in the plane if you measure them, is not yet organized. So the ability to develop this coordination is genetic, but the tuning is done in the first few years. So immobilization or anything. So the problem then is not to only work on the motor system, but is to work on these coordinating mechanisms. How is a problem which many people are working on. There is another thing, is that actually generating a locomotor trajectory apparently is something which one thing is related with coordinating muscle. No, it's not only. It has to do with gaze. Because if I want to turn, if I want to make a turn, I could make a turn like this. Or I could make a turn, but in fact, what the brain does, it makes a turn like this. Gaze initiates locomotor trajectory. The eye, then the head, then the trunk, then the feet. We have shown that by many papers. We have even a paper now recently accepted, I think, a week ago, because our friend Bill Warren said that our result was neither necessary nor sufficient. So when you publish in a good journal, and then you have a good friend who makes a paper saying that your result is neither necessary nor sufficient, then you have to prove that it is. So we did the same thing in the dark. So we had people walk in the dark, and if I walk in the dark like this, my eyes always precede my head and my trunk. So organization of locomotor trajectories is controlled by gaze. And the reason, if we go back to the previous reasoning, is that actually the brain generates the trajectory in some geometry, which drives the eye, then the head, and the trunk. So what has to be rehabilitated is gaze. And so the idea, which I submit to you, and we are working with clinicians trying to show that also, I will mention in PISA, that eventually one has to look very carefully at the gaze if one wants to look at these locomotor trajectories. So that is an example of the work we did a number of years ago with a scientist in Paris. This is a child going around a turn, and you see that the head is last 3.5 years, and at 5.5 years, the head, and we now have done the experiments. I have no time to go into these papers, but this is largely published. That actually, at that time, we could not have the eye. The eye goes first, even in the dark. Then there is another thing which is surprising, which makes us think. Let's suppose that I want to go around this table here. We start by here, and then I go around the table. I could do this in many ways. I could do that. I could do here. I could try to figure out this way, right? Oh, it's nice that they put this here, just for my demonstration. Thank you, Jens. So, in fact, what we observed and published in good journals, that's what people do. People do very stereotyped. This is the title of the paper with Ischer in Journal of Neurophysiology and in Journal of Neuroscience. People, a generation of locomotor trajectory, like hand movements actually, are very stereotyped, which suggests that there is actually probably optimizing principles. And we recently, with Daniel Benker, as I mentioned before, said that this is probably related to the fact that although we all think in Euclidean geometry, the brain uses affine, equiaffine geometries, complex geometries on which we are working. And that's interesting because once more it brings back the problem, which is apparently motor, into what I call a cognitive, but it's brain. So that's what the brain is about. So this is the name of the people. We have a mixture of roboticians, physiologists. This was done also with the group of Jean-Paul Lomont. And this is also why with Giovanni Cioni in Pisa, who has been so fantastic in giving me the chance now for nearly 8 years to work in Pisa with him, we have now developed some paradigms together to study the generation of locomotion in cerebral palsy children. And the paradigm is very simple, actually. The child starts from here, and he has to go to one lamp, if we light this lamp, or another lamp here, or another lamp. Very simple. The same paradigm as has been used in the literature for hand movements, with 3 targets. It's a nice paradigm because it allows us to study straight walking to a target, generation of a trajectory. You see here an example. We can look at the head anticipation. We cannot measure eye movements yet. Here you see the head which anticipates the turn. And we can also do what we are now writing up, which is the executive function. Like we light this light here, and when the child is here, we light this one. So he has to make the equivalent in the eye movement world of the antisaccade, which involves the prefrontal cortex. So it's a very interesting paradigm, which allows us to study many things, and anticipation. And also, Dr. Vittorio Belmonti, who will be talking on Friday about the magic carpet, another paradigm, which I will mention tomorrow morning, is here. And you can see his hand because there are 2 ways to work at these children. Kado, we've been discussing for many years with them. Some of them, as you know, are so-called perceptual children. They cannot walk. But if somebody is behind them without touching, suddenly they walk. And if they are hung like this somewhere, and they cannot get out from that, and somebody is behind them without touching, whoop, they touch. And I will mention tomorrow my ideas about that concerning spaces. So that is one example of an application of a few of the things we are trying to understand together with Giovanni and Vittorio. And this has been now published, and several other papers are published. So one of the hypotheses, which I will deal in detail tomorrow morning at the Castan lecture, is that these children are restricted to a body-centered space, and the presence, without touching, here Vittorio is touching, is guiding, allows them to shift to locomotor space. So these kids cannot jump from another space. But I will mention that tomorrow. Now, another very interesting property of our brain that we may think about when we try to rehabilitate these kids and adults too, is that the brain uses internal models to simulate action. They are built during early childhood, and so-called motor deficits may be due to deficits in this internal model. What are these internal models? These internal models are neural networks which are in the brain and which allow this internal simulation, like when you dream. I don't know if you dream. I have nightmares every day, every night, so I'm always happy as soon as I wake up. Every night I have nightmares. They all look perfectly real. I have a second life, completely. My body is there, you are there, my slides do not work, everything. The body has internal circuits which allow it to completely simulate without any sensory input. That is very important for rehabilitation. We do not need the world. It's a lie. I mean, in adults when we feel normal, right? Okay. Now, we have shown that with papers. This is published in Nature Neuroscience 2001. We went to space because Francesco Lacquaniti, I don't want to use your computer, but if I had a big bottle here, I would show you that if I let it fall, my hand does not move. In the child under 1 year of age, if a big load goes down, the hand does this. He waits until contact to answer. But in me, it doesn't. Because 100 milliseconds before the contact, the brain generates exactly the force which is needed to compensate. And this, it can only do that, as we showed with Lacquaniti, and they had many new papers on that, it can only do that if it has internal models of the effect of gravity, not only of my impedance, but also of the Newton law mechanics, which is what the child, the normal child, learns during his childhood. He builds these internal models not only of his body, but also of the laws of mechanics. So this is eventually what has to be rehabilitated. It's not only the muscular system, it's a consequence what happens to the muscles. And we did actually some work, this is published by Seno in Paris on the MEG, to show the difference in the brain between when you catch and when you don't catch the ball. The anticipation which happens at the level of the brain and not only the EMG. Now, let's go just one step further, and I'm not going to be very long. Am I already over? Not yet, says Ian. Thank you. We also have an internal model of our whole body. This is called the body scheme. It's in the literature. And we now know that eventually there is a crucial area where this body schema is constructed. This was known and described by Penfield many years ago, awareness of body scheme and spatial relationships in the parieto-temporal area here, which is also the vestibular cortex. It is the top of the vestibular system. So the vestibular system is not only to compensate gaze or posture, it is also the fundamental reference for our self. Okay? So this brain area is fundamental, but also all the superior temporal sulcus here. And we have shown that with, in France by electrical stimulation in epileptic patients inducing body movements. It has been also shown by Olaf Blanke here in Lausanne, who showed also the appearance of out-of-body experience when stimulation here. And Monica, I was interested by the fact that Monica Zilbovicius here showed hypoactivity in this area in autistic children. As if these children, it's a speculation, may not have the ability to construct this own body and relation with space. And I will talk tomorrow about the implication on social relations of these findings. I'd like just very quickly to mention the fact that there is also, we also have developed over the years a theory of scoliosis, vestibular origin. in some children having craniofacial asymmetry with Dr. Dominique Rousier in Lille. We have proposed a vestibular theory of scoliosis, not due to, because we have found in some of these patients having these live scoliosis, anomalies of the canals, which had not been done before. And at the same time, we had shown that these patients, if we ask them to do the classical test of the hands, I hope they are horizontal, they go like this. The theory here is that actually this scoliosis could be not vestibulospinal, but could be cognitively driven by a perturbed body scheme. So they would be compensatory, all right? Perceptively compensatory. And it has not been demonstrated, but in China, there is people working on that now. Now, the fact that we have this second body in our brain, this body scheme, is now being evidenced beautifully by experiments such as done by Blanke here, or by Ekstrom, and we have done some in our lab. You know that if you put a virtual glass on a person, take a picture of his back, so I have the camera here, so I would see myself in front of me. No, okay. So if I have a camera here, I would see myself, Berhoz here, like this guy. Here is a virtual person, and according to the same experiment like what was done with the la main de caoutchouc, the rubber hand, if you touch this person, if you would touch me, I would very quickly have the feeling that it is the virtual Berhoz which is touched. So this virtual body that we have is actually, we can export it outside in the world, and it's very important eventually that the rehabilitation takes into, I propose, takes into account the fact that we have a physical body, but we have also this other body which is essentially probably plastic, you would say, Michael, but modifiable. It is modified permanently. And I am now working, as many of the kids actually around us, with artists who have avatars. As you know, many of our young people now have avatars in virtual world. They live with these people, and it's remarkable how much they project themselves. For instance, Claire Sistak immersed herself. She made a virtual game with this avatar who lost everything. She had a depression, a real one. And then she made this one who won everything, and she got out of depression. The interesting thing is that today, if she looks at the picture, she depresses. So the avatar is here. Very interesting and important for a relation with these kids here today. I go quickly, and I will be finishing in one and a half slide. Okay? And this introduces me to what will be one of the topics of my talk tomorrow, because I have not only did Jens and the organizer take the risk of having me speak once, but even twice, which is a terrible challenge. So because I was talking about this problem, it is, of course, these experiments are done in first-person perspective. So you project your body outside. But there is now experiments concerning third-person perspective. And we, together with a group of psychologists in Paris, the group of Olivier Houdet, and particularly Grégoire Borst, who is a specialist of mental rotation, we have made a paper in which we have taken a classical paradigm of identification of the side in which somebody has a hand, which obliges you to change perspective. And we have adopted their paradigms, which I have no time to go into, which is a negative priming paradigm, to assess the importance of inhibitory control. And the result is that the growing ability for a child or an adult, but to adopt a third-person perspective, like putting myself in the seat of Jens to see if he really says his Berhoz going to end, which would require that I sit here in his seat, is in part, and probably empathy, that I will talk about, is rooted in part in their growing ability to inhibit the first person. And the general hypothesis is that if the child is enclosed in one PP, he will not develop tolerance, which we will go back to tomorrow. And I thank you very much.